When astronaut Scott Kelly returned to Earth after 340 days in the International Space Station, something impossible had happened. He was no longer the exact same age as his twin brother, Mark. Mark was older, not because of stress, not because of biology, but because for Scott, time literally slowed down. Exactly 8 milliseconds of his life vanished, and scientists knew this would happen before he even left the launch pad. This is not just space trivia, the exact same physics is warping the GPS satellites above your head right now. If engineers did not actively correct for it, the map on your phone would be off by 11 kilometers by the end of today. By the time this video is over, you will understand exactly how reality bends time, why we can predict it, and what it actually does to the people who live through it. Scott Kelly spent 340 days circling Earth at nearly 8 kilometers per second, fast enough to lap the planet every 90 minutes. His identical twin, Mark Kelly, stayed behind on the ground. For most families, a year apart is measured in missed birthdays or long-distance calls. For the Kellys, the separation became a living experiment in the physics of time itself. From the start, both brothers knew the numbers would be razor-thin. Scott's mission was timed and tracked to the second. Every heartbeat, every meal, every orbit was logged. But what no stopwatch could catch was the slow drift that would open between them. A gap written not in memories, but in the ticking of atomic clocks. NASA's scientists predicted it before Scott even launched. They warned him. After almost a year in orbit, he would return just a tiny bit younger than his brother. The difference would not come from exercise routines or space food. It would come from the way the universe bends time for moving bodies and for those closer or farther from Earth's pull. To most people, a few milliseconds means nothing, but for the Kelly twins, it was proof that time is not a fixed river. It can be stretched or squeezed depending on how you move and where you are. Their story is more than a curiosity. It is a test case for the deepest laws of nature and for the precision that modern science demands. Subscribe for more stories that bend the boundaries of what we think is possible. Two forces compete over every second that passes on the International Space Station. The first is speed. According to Einstein's special relativity, the faster you move, the slower your clock ticks compared to someone at rest. This is not just a metaphor. There is a formula for it. The Lorentz factor, written as gamma, tells us exactly how much time slows down for a moving object. Even at the station's blistering orbital velocity, the effect is subtle, but it is real. Motion drags on time, stretching each second just a hair longer for those in flight. But gravity has its own grip on time. Einstein's general relativity predicts that clocks run faster when they are farther from a massive body. On the station, astronauts are about 420 kilometers above Earth's surface. The pull of gravity is weaker there, so their clocks actually try to race ahead, ticking faster than those on the ground below. This is gravitational time dilation, and it can be measured with atomic clocks precise to a billionth of a second. The result is a tug of war. Speed slows the station crew's time down, while altitude tries to speed it up. For the station, velocity wins out, but only by a razor-thin margin. The math is not just theory, it lets scientists predict to the millisecond how much younger Scott Kelly would be after 340 days in orbit. The same equations run inside every GPS satellite, every navigation app, every experiment that ever sent a clock around the world. The universe keeps score, and now, so can we. Subscribe for more stories where science rewrites what we think is possible. Every orbit aboard the International Space Station is a real-world calculation in Einstein's math. The space station circles Earth at 7.66 kilometers per second, fast enough that special relativity predicts its clocks run a little slow. The formula isn't guesswork. At this velocity, the kinematic drag subtracts about 2.5 microseconds from each day, compared to a clock on the ground. But the story doesn't end there. Gravity too has a say. At 420 kilometers above Earth's surface, the station sits higher in the planet's gravitational field. Here, general relativity adds back about 1.6 microseconds per day, because clocks run faster, farther from gravity's pull. These two effects, one slowing time, one speeding it up, don't cancel perfectly. The numbers are precise. Subtract the gravitational gain from the kinematic loss, and you get a net difference of minus 0.9 microseconds per day. That's less than a millionth of a second, but it's measurable and it accumulates. Over Scott Kelly's 340-day mission, the total lag reaches about 8 milliseconds. This isn't a theoretical oddity. Atomic clocks aboard the space station and on the ground confirm it. The universe's bookkeeping is exact. Speed and gravity shape the passage of time, and for astronauts in low Earth orbit, velocity wins by the thinnest of margins. In higher orbits, the balance flips. But here on the space station, each day is a microsecond behind the world below. Subscribe for more stories where the numbers behind the science are stranger than fiction. 20,000 kilometers above Earth, every GPS satellite is locked in a different game of time. Up here, gravity is weaker than on the ground, so clocks are tempted to run fast, 45 microseconds faster each day. But the satellites are also moving at nearly 4 kilometers per second, and that motion drags their clocks back by 7 microseconds per day. Add it up, and the net gain is 38 microseconds per day, compared to clocks on Earth. That may sound trivial, but GPS navigation is unforgiving. Light travels nearly 11 kilometers in 38 microseconds. If engineers ignored this, your phone's map would drift by the width of a city every single day. To prevent disaster, each GPS satellite is built with its atomic clock set to tick slower on the ground, deliberately offset by exactly the amount relativity demands. Only then, once in orbit, do the numbers align. Relativity is not a footnote, it is the reason GPS works at all. Subscribe for more stories where physics guides your every step. In 1971, physicists Joseph Hafele and Richard Keating set out to measure Einstein's predictions in the real world, not in a lab, but on commercial jets. They packed 4 cesium atomic clocks and flew them twice around the globe, once eastward and once westward, always at cruising altitude. Each leg pitted speed against gravity over thousands of kilometers. When the clocks returned to the US Naval Observatory, the results were undeniable. The eastbound clocks, racing in the direction of Earth's rotation, lost 59 nanoseconds compared to those left behind. The westbound clocks, moving against the spin, gained 273 nanoseconds. These numbers matched the theory within a hair's breadth. Every tick and tock played out in the open, on passenger jets, not in isolation. For the first time, relativity's tug-of-war showed up in the nanoseconds, exactly as predicted. The Hafele and Keating flights proved that time can slip even for travelers in ordinary seats, and that the universe keeps score with precision. The next time you check your watch in an airport, remember, every journey is a test of time itself. Subscribe for more stories where numbers rewrite what we know about reality. 8 milliseconds. That's the age gap etched into the Kelly twins story. A difference so small it slips past ordinary senses, yet large enough to be measured by the world's most precise clocks. Russian cosmonaut Oleg Kononenko, after 1,111 days in orbit, stretches that lead to 27 milliseconds. The record for human time travel is not a leap, but a blink. Yet the story doesn't stop with clocks. On Scott Kelly's return, scientists found his white blood cell telomeres had lengthened by 14.5%, a possible stress response to radiation and microgravity. But this biological shift faded within days, while the millisecond age gap remained. DNA damage, short telomeres, and other markers remind us that physical time and biological aging are not the same. Both are real. Both are written into the astronaut's body. Now imagine what happens if a crew could accelerate at 1g, Earth gravity, for a full year. The math is relentless. After 1 year on the ship, they would reach 77% of the speed of light. For those on Earth, 1.19 years would pass. In that time, the ship would cover more than half a light year. The numbers explode, and so does the imagination. The laws that make Scott Kelly 8 milliseconds younger could, one day, let future travelers leap centuries or millennia into the cosmic future. Subscribe for more stories where science stretches the boundaries of time. Every millisecond in orbit is a test of reality. Scott Kelly's 8 milliseconds. GPS with 38 microseconds per day. Oleg Kononenko's 27 milliseconds. Time splits, but so does biology. As humanity dreams of accelerating beyond Earth, these numbers are not trivia. They set the limits for our future. Subscribe for the next leap.